In the last lecture, we introduced a density theorem, namely that the set of CR embeddings is dense in the set of CR proper maps for the strong topology when the dimension of the target space is greater or equal than 2 times the dimension of the source space plus 1. In this lecture, we are going to discuss the proof of this theorem that has as a corollary the Whitney embedding theorem. Let us recall the statement of the theorem. Let M and M be CR manifolds where R is greater or equal than 1 and less or equal than infinity. Suppose that the dimension of the target space is greater or equal than twice the dimension of the source space plus 1. Then the theorem says that the set of CR embeddings is dense in the set of CR proper maps for the strong topology. Of course, when M is compact, any continuous map from M to N is automatically proper, and so in particular the theorem says in that case that for M compact, the set of CR embeddings is dense in the set of CR maps for the strong topology. Let F0 be a proper map from M to N, right? Okay, and now let N be an open neighborhood of F0 such that N is contained in the space of proper maps. This is possible because the space of proper maps is open, right? What we want now, okay, to find an embedding in N. In this way, it could be clear that the set of embeddings is dense in the set of proper maps, because given actually any open neighborhood of a map, we can find there an embedding. And it suffices to show that there exists an injective immersion in this set N. Immersion. And why is that? Because N is contained in the set of proper maps. And injective proper immersions are indeed embeddings. We are going to consider, okay, locally finite cover of M by compact sets. And indeed, we are going to assume that Ki is always contained in a domain of a local chart. Okay? This is possible by considering the Ki's small enough. Right? Now we can define the following set Xi, which is the maps that belong to N and that are embeddings in a neighborhood of Ki, right? And what we want to prove is that this Xi is and open and dense subset of M. Okay? One of the properties is obvious. Xi is open because embeddings are open in the strong topology. So this is not going to be an issue. What remains to be proved is that Xi is a dense subset of M. So consider a map F in N. What we want to prove is that any open neighborhood of F for the strong topology contains an element of Xi. Okay? Very good. Let us assume that the image of Ki by F is contained in some Wi, where Wi is just the domain of a local chart. Okay? Very good. Let us see how we can approximate F by maps that are embeddings in a neighborhood of Ki. So consider Ki, which is going to be containing Ki prime. Ki prime is a compact set, which is going to be contained in Ui tilde, which is going to be contained in Ui. These two sets over here are open sets. Okay, we are going to require that Ki is contained in the interior of Ki prime, and also that the image of Ui tilde is contained in Wi. This is possible by considering a small compact neighborhood of Ki, which is contained in a small open neighborhood of Ki, right? What happens now is that we can consider the local expression of F in the local charts phi I and psi I. Okay, and this is a CR map which is defined in the image by the local chart phi I of Ui tilde, indeed in general in a bigger open set, but in particular in this one, and whose image goes to Rn, okay? Whose image is contained in Rn, right? And what we know is that because of Whitney approximation theorem, right, we can approximate this local expression of F by a map Gi, okay, which is going to be also of the same, belonging to the same space of maps in the weak topology. Such that Ji is an embedding, well, such that Gi is an embedding. Okay, we can do this because of the Whitney approximation theorem and the Whitney embedding theorem for submanifolds of Euclidean spaces, right? What we want now is a little bit more than this, okay? Because what we want is to approximate F in the weak topology, but indeed it's going to be an approximation in the strong topology by a map, I don't know, we want to approximate in the weak topology by a map that coincides with F outside Ki prime and is an embedding in the neighborhood of Ki. And if we can do this, these approximations in the weak topology are going to be approximations also in the strong topology, because all our approximations are equal except maybe in the points of a compact set. So in this case, the approximations in the weak and strong topology are equivalent, okay? If we have a sequence of maps that converge in the weak topology, but that are all equal outside of a compact set, they converge in the strong topology, right? So we don't have this so far because the Whitney approximation theorem gives us approximations of F, or if you prefer, of the local expression of F. Okay. We have this thing, which is a CR map, okay, from the image by phi of ui tilde to Rn, right? And what we need actually is to approximate this local expression in the weak topology by a map that coincides with the local expression outside of the image of Ki prime by phi I. And it's an embedding in a neighborhood of phi I of Ki, right? Okay. As we know, we have these approximations of the local expression. We have this approximation, but we can make this approximation as good as we want. But the approximation does not satisfy the condition, this condition over here, that the approximation coincides with the map outside of Ki prime. So in order to obtain that condition, let us consider a map, lambda I, a C-infinity map, from the open set phi I of ui tilde to the closed interval 0, 1, such that lambda I is equal to 1 in a neighborhood of the image by the local chart of Ki, and the support of lambda I is contained in the image by the local chart of Ki prime, right? And there We define capital GI as 1 minus lambda I times the local expression of f plus lambda I times GI. We have that the capital GI and the small gi coincide in a neighborhood of phi I of ki, right? And in particular, that implies that the capital GI is an embedding in a neighborhood of such a set, okay? Besides that, we have that capital GI is equal to the local expression of f outside phi I of ki prime, okay? And since we can consider ji in an arbitrary open neighborhood of the local expression for the weak topology, we can consider that capital GI is in an arbitrary open neighborhood of the local expression for the strong topology, right? Very good. Now, what can we do? We just define a map H from M to N. The restriction to UI tilde is going to be just this map over here, and the restriction to the complement of such a set is just F. And in that way, we obtain, since GI is an approximation of this map as good as desired in the strong topology, so H is an approximation of F as good as desired also in the strong topology. So in particular, we can choose H in any neighborhood of F for the strong topology, right? Okay, very well. But it is clear that this map H belongs to Xi, right? Because since capital GI is an embedding in a neighborhood of phi I of ki, because of this formula, H is going to be an embedding in the neighborhood of ki. So H belongs by definition of Xi to Xi. And so what we are proving is that in the neighborhood of every map in N, there is, in any neighborhood for the strong topology of any map in N, we have a map in Xi. So in particular, we deduce that Xi is an open and dense subset of M. Let's recall that Xi is the set of maps of N such that G is an embedding in a neighborhood of Ki. Okay? This is the definition. Now, okay, this is assuming that that the image of Ki is contained in a local chart of M, but if that is not happening, if that doesn't hold true, what we can do, is dividing Ki in a finite number of compact subsets such that the image of every one of them is contained in a local chart and adapting this argument that we just did. And that's doable. It's a reasonable, simple adaptation. Okay, so we have that this Xi is an open and dense subset, of N. We can consider another case when Ki does not intersect Kj. And in that case, we can define Xij as the set of maps in N such that G is an embedding in a neighborhood of the union, okay? Again, by adapting the previous argument, we can see that Xij is a dense open subset of M. Very good. We are going to define for every R a locally finite covered by compact sets. Okay, for any R, for any natural number. And we want that every of the compact sets that we're considering is contained in some Kj. The Kj's are the sets, the compact sets that we already consider. We already consider one locally finite cover of our manifold by compact sets, locally finite cover of M. Okay. We want this property and we want an additional property. Intuitively, what we want is that as R goes to infinity, these sets in our compact cover have to be smaller and smaller. So what we're going to require is that if X and Y are points in M such that X is different than Y, then there exist two compact sets in one of these compact covers. So we have K sub I super R that has empty intersection with K sub J super R, and such that X belongs to the first compact set and Y belongs to the second compact set, right? And now we are going to consider the following set. The intersection of Xij super R intersection with the all the Xi's. Okay, of course we are considering these sets just when this intersection is empty. Okay, so what can we say about this intersection? The first thing that we want, okay, it's intersection. Let's write it down again. The first thing that we should say is that an open subset of a Burr space is also a Burr space. Okay, this is going to be very useful, and it is a general property of pair spaces. In particular, our N, which is an open set for the strong topology, is a pair space. Okay, that is good. What happens now is that all these sets that we are considering over here are indeed open and dense subsets of M. Okay, so let's call this set over here, I don't know, Y. Since we have an intersection of open and dense sets in a Baire space, that means that Y is dense in M. Okay? So in particular, we have that there exists a map, I don't know how we can call this map, let's see, alpha, for instance. Let's go with alpha. There exists a map alpha in Y intersection N, right? And what we want to see is that this map is an embedding, right? Alpha is a proper map. This is because alpha belongs to N and all the maps in N are proper maps. So yeah, alpha is also a proper map. Besides that, alpha by construction, because it belongs to xi for every I, alpha is an embedding in the neighborhood of ki for every I. But in particular, it's going to be an immersion in the neighborhood of every point. So alpha is an immersion. And what we are going to check out next is that alpha is injective. Indeed, consider 2 points in M such that X is different than Y, right? Because of our construction, we have 2 compact sets, K sub I super R and K sub J super R, that have empty intersection, but such that X is an element of our first compact set and Y is an element of the second compact set, right? Now, we know that our map alpha is an element of X sub ij super R. And in particular, that implies that alpha is an embedding in a neighborhood, by definition of that set, in a neighborhood of the union of the set K sub I super R and K sub J super R. But that implies that alpha is injective in that set. And since X and Y belong to that set, we get that alpha of X is different than alpha of Y. So if we have 2 different points, the images by alpha are different, so alpha is injective. If we actually take a look to everything that we proved, we saw that alpha is a proper map that is, an immersion, and that is injective. And an injective proper immersion is an embedding. So we get that alpha is an embedding. And that's it. We proved what we wanted. So we actually proved that the set of CR embeddings is dense in the set of CR proper maps. In the next lecture, we are going to revisit the concept of transversality of a differentiable map to a submanifold. And indeed, we will analyze the properties of transversality within the framework of the strong topology. Thank you for your attention.